video, I'm going to do some more from 6.3. So 6.3, we introduced the fundamental theorem of calculus, both part 1 and 2. This is still going to be using the fundamental theorem of calculus. So we saw this, that if I'm evaluating a definite integral of some function, it's the antiderivative substituting in that upper bound, and then minus the antiderivative and substituting in that lower bound. Now, if the integrand, remember this part of an integral is called the integrand. So if the integrand is a derivative, well, remember the antiderivative of a derivative is just the original function. So the antiderivative of f prime is f. So it's the same exact thing, right? The antiderivative plugging in the upper, antiderivative plugging in the lower, okay? Now, I could add f of a to both sides. This is an equation, so I can rearrange it, right, as long as I do the same thing to both sides. So f of a plus this integral is equal to f of b. So it's still saying the same thing, it's just been rearranged, okay? We're going to use this form quite a bit today, so we're just going to get familiar with that rearranging. Okay, so suppose f is a differentiable function whose derivative is this. If f of 1 equals 5, find f of 3. So I'm given a derivative function. I want to know something about the original function. So remember, the antiderivative of f prime is f. So I'm going to use an integral, okay? And I'm going to write it this way first. So we have the integral. I'm going to use these values that they gave me as my upper and lower. So 1's the lower, 3 is the upper, of f prime of x dx. Now, according to this, right, is equal to f of b minus f of a. Now, I'm specifically looking for f of 3, so I'm going to add that f of 1 to the other side. And then I'm going to essentially be using this, right? So f of 3 is equal to f of 1 plus this integral. And I'm going to go ahead and put in the 3x squared plus 4 dx. Okay, so now to actually figure out what this is, we already know f of 1. That was given to us. It's just 5, so the 5 is here. Okay, and now I need to find the antiderivative of this, right? So if this is f prime, I need to find what was f. So I use my opposite power rule, right? I add 1 to the exponent and divide by that exponent, so we should get x cubed. Antiderivative of 4 is 4x. So I'm evaluating, and you guys will see this notation where they'll put like just a vertical line with our upper and lower limits here and this says I'm going to evaluate this function for 1 and for 3. So that notation you'll see. Okay, so we still have that 5 out front. I am now doing this piece, right? I'm doing f of 3 minus f of 1. So plugging in 3, we got 3 cubed plus 4 times 3, and then minus, now substituting in 1, so we got 1 cubed plus 4 times 1. Okay, simplifying here, so I've got 5 plus, what do we got, 27 plus 12 is 39, and then over here 1 plus 4 is 5, so actually the 5's nicely canceled there, and I'm just left with 39. Okay, so that f of 3 is equal to 39. Okay, so we have worked a lot with position, acceleration, velocity, and we know that velocity is the derivative of position and acceleration is the derivative of velocity. If we go other way, we can say velocity is the antiderivative of acceleration and position is the antiderivative of velocity. So this form, you guys, where I'm kind of looking for one piece is really helpful when we're given an initial condition. So an initial condition is something like this. They give me f of 1 was 5. Here they're giving me v of 0 is 150. That is an initial condition, something about the original function that I know has to be true. So, and sorry, this is a typo. This should be 10e to the t. Okay, so I have the acceleration function. If the initial velocity v of 0 is 150 meters per second, what's the velocity of the object at time d? So velocity is the antiderivative of acceleration. So I am going to write, I'm looking for v of t, okay, and I'm again going to kind of use this form. The initial piece we're given is v of 0. Okay, so this one, the lower bound is 0, but this time I wasn't given another number to find, so I'm just going to use t because I'm asking about time t. And then here, I am going to find the antiderivative of acceleration because that is velocity. So I'm going to put this in here, 10e to the t. And actually, I'm not going to use t because I'm going to end up plugging in t. So I'm going to use something else. I'm going to use u here. So we'll do u and then du. Okay, so now I'm going to do what I know. I'm going to plug in my 150 for v of 0. This, the antiderivative of 10e to the u is itself. So we're going to evaluate 10e to the u between 0 and t. So I still got the 150. Okay, so plugging in t, we get 10e to the t minus 10e to the 0. So I get 10 times 1, which is 10. 150 minus 10 is 140. So my v of t equals 140 plus 10e to the t. All right, so our next question on the next page is still dealing with this question, but they are asking us about position. So we just found velocity. I'm just going to rewrite that here because we're going to use it in a second. So our velocity was 140 plus 10e to the t. Okay, this one is asking us about position, and this time they do give me a specific number to find. So I'm trying to find what is s. S is our position function. So I'm trying to find s of 2. Okay, they give me an initial condition. Okay, my upper and lower bounds, 0 is the lower. They do want me to find 2, so I do have a number to put in for my upper. And then we want the antiderivative of velocity to get position. So I'm going to put my velocity function right here, 140 plus 10 e to the t dt. Okay, so now the antiderivative is going to be position. So what is the antiderivative of this? Well, 140t plus 10e to the t. Okay, so now I'm going to substitute the things I know. So s of 0 is just 0. Then the antiderivative is this. So we're going to evaluate 140t plus 10e to the t. And we're going to evaluate that between 0 and 2. So 0 goes away, right? And this first part is 10 times, oh, sorry, not 10, 140. 140 times 2 minus plus 10e squared. And then minus, now I'm plugging in 0, so 140 times 0 plus 10e to the 0. Okay, so here I get 280 plus, I'm just going to leave that as 10e squared. That's 0, that's 10, so minus 10. So I get s of 2 equals 270 plus 10e squared. I could turn this to a decimal as well, you guys. If I wanted to, I'm just going to leave it like that. Okay. The population, different example now. The population is growing at a rate, right? Derivative makes sense because that's always a rate of change. So we're talking about a population change, and we're given the rate of change is this function. And our unit is million people per year. T is our number of years starting at 2020. Okay, so they want us to find the definite integral of p prime of t. So the antiderivative of p prime is p. Okay, so we need to know what is the antiderivative of this function. This is an antiderivative rule you guys need to know. This was, I think, in our antiderivative table back in chapter 5. But as a reminder, if my original function is a to the x, so a not being e, anything besides e, like 2 to the x, 1/2 to the x, anything like that, its antiderivative is itself divided by natural log of whatever that base is, okay? So in this case, I'm going to apply this rule. So my constant multiple is just going to stay there, just like the 10 stayed here with the e to the t. Same idea. The constant multiple stays out front. Okay, now this is this function, right? So that's my a. So I'm going to find its antiderivative by doing this. So it's itself, so 1.005 to the t divided by natural log of 1.005. Okay, so that is my antiderivative. So we are going to evaluate this using our fundamental theorem of calculus. So antiderivative plugging in the upper, antiderivative plugging in the lower, subtract. Okay? So when I substitute it in, I'm going to write it out just so you guys can see it. So, yeah, okay, so I'm just going to put equals down here. So we got 2.867, 1.005 to the 5th, divided by natural log of 1.005, minus 2.867 times 1.005 to the 0, all over natural log of 1.005. So I just plugged in my upper here for t and then my lower. Okay, when I calculate a problem, plug that in, what you guys end up getting is approximately 14.515. Okay, and then part B is asking us to interpret this answer. What does this mean? Okay, so we just found the derivative was a rate of change. So we found in millions of people per year. So we found the number of people. If you guys think about, I'm just going to rewrite that integral really quick. We had a couple problems like this on our last assignment. The units here are million people per year, right? And then t, the change in time, is years, right? So years is going to cancel, and we're going to just be left with million of people. So that's our unit for this number, okay, is 14.515 million people. Now, I should also talk about what the heck the 0 and 5 represented. So remember, 0 was our starting point, 2020. So from 2020 to 25, the population is projected to increase by this many million people. So that's what I'm going to write. So the population of the U.S. is projected to increase 14.515 million people. And then here's where I can include from 2020 to 2025. Okay? All right. Last part here. The population of the U.S. was approximately 33 million people in 2020. This is an initial condition. That is telling us what is P of 0 right there, okay? What is the projected population in 2025? Okay, so we want what is P of 5. Okay, so I'm going to use my kind of rearranged equation. Initial condition is P of 0. Plus, and then we're looking again 0 to 5, right, 2020 to 2025, of our P prime of t dt. Well, we already evaluated this, you guys. This was part A. So we got this from part A, so 14.515 from part A. And then this right here is given to me as 336. Okay, so I just add those together, and we get our P of 5 to be 350.515 million people. Okay? All right, we got one last problem we're going to look at here, you guys. Okay, so we have the graph, f of t is sine t from 0 to 2 pi. That should look very familiar, hopefully. We can be asked to find an accumulation function. So what this is like, what is my accumulated area under the curve of our function, okay? Now, the area under a curve is represented by an integral. So our function, and they want us to use g, so I'm just going to write that. So our function g of x, I'll put as g of x. Okay. Equals, okay, so I'm going to start at 0. I'm going to use this as my lower bound. You might think we're going to use 2 pi as our upper bound. That would give me the overall accumulation from 0 to 2 pi. But if you guys look ahead to part B, they're going to actually want me to evaluate it less than 2 pi. From 0 to pi over 2, from 0 to pi, from 0 to 3 pi over 2, and then 2 pi. So I'm actually just going to leave this as a variable, as x, because I can plug in some different things there for my upper bound. And then our function is sine of t dt. Okay, so this suffices. This is great. That is our accumulation function. I'm going to go a step further because I'm going to actually have to plug some things in for G. So I'm going to use the fundamental theorem, and this is going to be the antiderivative of sine, which is negative cosine, right, evaluated at 0 and x. So that is going to be negative cosine x minus negative cosine 0. That's going to turn to addition, right? So I got negative cosine x, and then cosine of 0 is 1. So this is another way I can write that accumulation function. That's just going to make this part way easier, okay? Because now I'm asked to find some different values. So I'm going to plug in pi over 2 into this function, pi into this function, 3 pi over 2, and 2 pi. Okay, so if I plug these in here, let's see here, we get pi over 2 is 0 plus 1, so I get 1 there. Pi is negative 1, so negative 1 is 1, plus 1 is 2. 3 pi over 2 is 0, plus 1 is 1. And then 2 pi is 1, so I get negative 1 plus 1, which is 0. Okay, so interpret. Okay, so from 0 to pi, this is all positive area, right? So as I am accumulating area from 0 to pi, I'm increasing, right? And then this is negative area, because it's below the x-axis. So as I start adding this negative area to this, I start going back down. Oh, and sorry, this should be 0. And then once I get to 2 pi, this area and this area totally cancel out, and we're left with just 0, okay? So I'm just going to say the accumulation of area increases, and I'm going to say from 0 to pi. Then decreases all the way to 0. So the net accumulation over our interval, I guess I'll do that, is 0. So again, the net is just our net change, right? Okay, so again, the positive area and negative area are going to cancel, which is why I'm left with 0. It was positive and increasing here because we only had positive area, okay? All right, that's it for this video, you guys. Thanks for watching.